Hi there and welcome back. This video concludes our discussion of recursion in SQL. And this video will be about a completely different use case. If you look at the recent videos, well, we were talking about cellular automata, we were talking about algorithms from computer graphics or machine learning. This is about something that is really classical in computer science, and it will be about parsing. Parsing strings, giving a context-free grammar that describes the valid inputs. Okay, so we've already discussed parsing regarding regular expressions. Regular expressions led us to deterministic finite state machines, and we could implement those in recursive SQL. But this will be about a more expressive formalism of parsing. It's about context-free grammars. Almost all programming languages out there could be expressed in context-free grammars. And given the discussion in this particular video, by the end of this video, we will see that such parsing tasks could also be completed by SQL. So parsing may be a sub-problem that occurs in a lot of data ingestion, data import, and data analysis tasks, and it may make sense to have parsing functionality embedded into a SQL application. And it will save us from using external parsers and shifting inputs from the database out to an external parser, have it parsed there, and then shift the result of the parse back into the database with all the serialization, deserialization, and efficiency problems that come with this approach. This video will give us all the tools to perform parsing in database, close to the data. All right, let us refresh the vocabulary that comes with context-free grammar. So I'm assuming that all of you guys know about context-free grammars and parsing with context-free grammars. This is just to align the terminology here. Okay, well, context-free grammars are given as a set of so-called production rules. Production rules have a left-hand side and a right-hand side. Okay, so left-hand sides are the so-called terminal, or are comprised of non-terminal symbols. There's one dedicated non-terminal symbol here. In this case, it's the expression symbol, the so-called start symbol, that stands for the accepted language. Okay, on the right-hand side of this arrow here, of this production rule, we will see the acceptable forms of any string, of any program, or whatever we are parsing in our context-free language. Okay, so as you can see in this very simple example, there are two acceptable forms of input that is described by this production rule. You see this vertical bar here, it indicates a choice. All right, so that would be an acceptable form of the input, and a term, another non-terminal, would be also an acceptable form of the input. And of course, there will be further production rules that tell us how a term might be structured. It itself might have interesting structure of one of two forms. It may be a term recursively, then a mult and a fact. So let's look up the production rules for mult and fact. There are here below. Mult, okay, so this simply stands for a multiplication symbol. So what we see here on the right hand side, more focus, that would be a terminal symbol, a real symbol, a character maybe that is occurring in the programs, in the strings that you would like to parse. So these are the terminals. They don't have further recursive structure. Okay, so what this tells us here is a term might be introduced by a term again, followed by a multiplication symbol, okay, followed by a factor or a fact here. And you see the fact indeed also immediately resolves to a terminal, just the symbol 1 here. This is on our slides in our very simple sample grammar here. Just represents any numeric literal. We are content with just the number 1 here, just for simplicity reasons. Okay, so a multiplication symbol followed by the symbol 1, that would make up for one acceptable term. Another form of acceptable term would be just a factor, so just the single symbol, the symbol terminal one would also be an acceptable term. This is how to read these context-free grammars. All right. Well, this particular sample grammar here, this example grammar, it already defines something useful. It defines a grammar for very simple arithmetic expressions that can feature two operators, the addition and multiplication operators. You see both are occurring as terminals here. And as I told you, only consisting of the literal one. And we could easily extend the grammar, of course, to accept any numeric literal here in this place. The grammar is structured such that the associativity of the binary operators plus and multiplication is indeed associating to the left. All right, you can see this by the occurrence of the recursive non-terminals here. So these are left recursive rules, as they are called, and this leads to a left associative interpretation of these binary operation symbols. All right, so that would be the usual interpretation in more complex arithmetic expressions. And this grammar also incorporates and encodes operator precedence. So multiplication precedes summation, and this is also included in this particular grammar simply by the layering of these rules. So this would be the rule that is concerned with additive terms. This is the rule that is concerned with multiplicative terms. They are layered in this particular fashion with expression, the additive terms building the top level here, and this leads to the desired operator precedence, as we will also see on the upcoming slides. So quite some stuff already packed into this very simple sample grammar here. Okay. When we will talk about grammars in the following slides, and when we will transcribe this grammar and its processing into SQL, then we will assume that this context-free grammar is given in Chomsky normal form. Okay, so in Chomsky normal form, the form of production rules is restricted. As you can see, this would be the same sample grammar that we've just seen on the previous slide in Chomsky normal form. It also talks about expressions and terms and products and additive terms, such sums here. But, well, we had to adapt for Chomsky normal form, and that means that production rules may only be of one of two forms, all right? Either we have rules of this form in which a non-terminal maps immediately to a single terminal, okay? Or we have the rules of this form where a non-terminal, like expression, maps to exactly two other non-terminals. All right, as you can see, this leads to the splitting of the right-hand sides of some of the longer right-hand sides that we've seen on the previous slides, but it's actually a very simple translation or transformation process that brings us from the general context-free grammars into the Chomsky normal form. The Chomsky normal form will help us to find a regular, simple tabular encoding of this grammar in form of a relation or a table. Okay. Yeah. So what else? Well, the output of such an analysis of an input string given a context-free grammar is either just a Boolean flag that says, hey, this input string is indeed valid according to the start symbol of this context-free grammar. This input string can be derived or can be generated from the start symbol of the context-free grammar. That could be one result of a parse. The other result of a parse could be a parse tree in which we can relate the symbols of our input. This would be our input arithmetic expression. I've reproduced this here at the top. Okay, we can relate this input arithmetic expression with the non-terminals that produce parts of it. Okay, so this one here, this part of the one, has actually been produced by the non-terminal expression. All right, and well, why could we produce this non-terminal one from expression? Because there is an according rule in the grammar. This is the rule that allows us to do that. All right, likewise, we could derive the plus symbol from the plus non-terminal or the multiplication symbol from the multiplication non-terminal. You see all these rules present here on the left-hand side in the grammar. Okay, so on the upper layers on the tree, we see that the tree says that we could derive the prod non-terminal from the sequence of the mult and the fact non-terminal. Okay, so prod, mult, fact, indeed, this is one of the rules that is specified in the grammar here. As we move up the tree, we find non-terminals that are derived from their right-hand side. So a terminal, a term could be derived here because there is a left-hand side term and then a right-hand side product. Okay, and this is exactly this particular rule that has been used to derive term here. So as we move up the tree, we move bottom up. We move from the very input, the character symbols in our input string, up to a layer of non-terminals that we could derive here, up to another layer of non-terminals that we could derive, up to another layer, until we reached the root of the tree, where we indeed were able to derive the start symbol of the grammar. Expression is the start symbol of the grammar that describes the valid input language. When we can derive the start symbol of the grammar from the entire input that we were given, then this indicates a successful parse. We will come back to that, but this is how to read these parse trees, right? So given the input, bottom up, we derive non-terminals. Other non-terminals are derived from sequences of non-terminals, right? And so on until we can derive the start symbol. All right. So now that we have restricted our grammars to Chomsky normal form, it's very easy to find the tabular encoding of the production rules. So this would be a table that encodes the production rules that you've just seen on the previous slides. That table would just have a column LHS, left-hand side, that would hold the non-terminals on the left-hand side of the production rules. And then it would encode the right-hand sides, which can only be of two forms. There's the particular form where the right-hand side only consists of a terminal symbol, and that would be one such rule. And the plus row above would also be one rule of this particular kind. You see that for such terminal rules or rules that immediately lead to terminals, the sim column carries the terminal symbol that can be derived from the left-hand side. Okay, and in this case, the right-hand sides, these two right-hand sides are simply set to null. All right. Other rules, like the prod rule here, allow to derive from this particular non-terminal two other non-terminals, in this case mult and fact. So here we set the terminal sim to null and then simply list the names of the derivable non-terminals here in the right-hand side 1 and right-hand side 2 columns. And of course these refer to, well, their respective non-terminals here in the column LHS. You can see that choice is being implemented by simply repeating non-terminals in the left-hand side column here. And this in fact means that there are three possibilities to derive the expression non-terminal from these particular right-hand sides. So 3 choices are encoded in the table here. And if I flip back one slide and look at the Chomsky normal form grammar again, you see exactly these 3 choices represented in the grammar as well. Okay, so given Chomsky normal form, mapping this particular grammar into its tabular form really is very straightforward. Okay. Again, we have an embedded functional dependency here, and we used that embedded functional dependency simply to encode whether a given left-hand side non-terminal symbol is indeed a start symbol. There is only one start symbol in our sample grammar. It's the expression non-terminal, and you see exactly in these 3 rows where we define expression, we indeed find the start boolean here, which indicates the start symbol, to be true. In all other cases, these left-hand side non-terminals are indicated as not being start symbols. Again, there is some redundancy here, and we happily accept that because it simplifies the encoding and the processing of this table. All right. Given this grammar, I think we can already sketch the parsing process that we are trying to implement. Again, it will be dominated by an invariant, as we have done so many times already in our discussion of recursive queries. Okay, so we will build a recursive common table expression to implement the parsing, and the recursive common table expression will emit a table of this form, a 3-column table. All right, and in this 3-column table, an entry LHS from 2 will indicate that we could derive the non-terminal in the LHS column from the input string at indices from 2. Okay, with indices I simply refer to the character indices in our input string. So in our input there will be the first character, the second character, the last character. These are the indices I'm talking about when I'm looking at the from and to columns here. So to indicate or to encode this successful parse tree using this invariant, well, indeed we see that from the character at index position 1, only from this particular character where there was a literal 1, we could derive the non-terminal expression. And this is indeed what we find here in the table. So from the character that is at position 1 to 1, so it's really only the character at position 1, we could derive the expression non-terminal. Let's look at another example. So at position 4, there's the multiplication symbol. From that, we could derive the multiplication non-terminal. Okay, let's see. Yes, it's here. Okay. So indeed, this lower layer of the parse tree is already represented here in this table that we will build by the recursive CTE. Let me draw a line here. Everything above this line actually refers to what you see below this line in the parse tree. So these are the basic parsing derivations that we have made that were directly made from individual characters in our input here. Everything below this line in the table and above this line in the parse tree represents derivations that have been made not from terminals but from non-terminals. So as you can see, the prod non-terminal that could be derived here, it's located here in the parse tree, has indeed been derived from the characters that were located at positions 4 to 5. All right, so the characters at positions 4 to 5 together were used to derive mult and fact, which then could be used to derive prod. And indeed, prod could be derived from the parts of the input that were located from indices 4 to 5. This is how to read this parsing table. As we go up the tree, there's indeed term that could be derived from characters that started at 3 to 5 inclusive. And indeed, term could be derived from character 3 to 5 inclusive. Of course, most interesting is the start symbol here at the root of the parse tree. And indeed, we find an entry for the start symbol. It could be derived from the input at position 1 up to position 5, which spans the entire input. All right, so from position 1 to position 5, this is the entire input. The entire input could be used in multiple steps, in multiple tree layers, so to say, to derive the start symbol, which indicates a successful parse. Okay. So this is look at the same table, actually. Here we will indeed call it the parse table, because this is what we will call it when we construct our recursive CTE. And this is the same parse tree again. I have now indicated the layers. Of the tree for a particular reason, because we will discover the entries or the nodes in these layers in this bottom-up fashion, as I told you already, starting at layer 0 and then advancing through layer 1, 2, 3 up to the topmost layer 4. All right, so let's draw the line again. And we will see in our recursive common table expression that indeed the layers correspond with the iterations of our recursive common table expression. So everything that is found in layer 0 here will indeed be found by the base case query, Q0 already of our recursive common table expression. So it's found in iteration 0 in a sense. All of these facts are already found in iteration 0. All right. Once we know that mult and fact could be derived, we are in the position to then, in the next iteration, to derive prod. So prod will be found in iteration 1, and indeed it's found in layer 1 of our parse tree. Okay, so given facts that we have derived in iteration 0, when we can derive facts that are located in iteration 1 here. Okay, so far so good. That's how recursive common table expressions work. In a subsequent iteration, we can see what has been derived immediately before that iteration. Okay, so iteration 1 can see what has been derived in iteration 0. All right. So how about layer 2 here? How about layer 2 and this term non-terminal? We would like to derive that, and what we need is, of course, the knowledge that we could derive prod at some point, and we need the knowledge that we could derive term at some point. And here is where a problem occurs. As you can see, prod is just one layer apart from term, but this term non-terminal is 2 layers apart, and thus 2 iterations apart from our term non-terminal here. Okay, is this a problem? Well, yes, it's a problem, because when we are in iteration 2 of our recursive common table expression, all that we see in the working table parse of our common table expression will be what has been derived in the iteration before the second iteration. So all we can see indeed is what has been derived in layer 1. And that's not enough. That's not enough to indeed derive the term non-terminal. We would have to have memory. We have a memory that 2 iterations ago, term has been derived. And it will get worse for the upper layers. To derive the sum to non-terminal, we would have to have knowledge about the non-terminal that has been derived in the iteration or in the layer immediately before that. That's fine. But we would also need long-term memory to remember that plus back then has been derived in layer 0 or iteration 0, which is equivalent to say. So, but this is something that would not be present in the working table when we are in iteration 3. So this is also mentioned back down here in this bullet point, and indeed it's a problem for our parsing approach here. Keeping only the results that have been produced in the most recent iteration can be a challenge for a computation that needs to have long-term memory in a sense and needs to remember what has been derived in iteration 0, iteration 1, and in general results that have been derived in some iterations apart. Here's another view of the problem. So if you are in the first iteration of our iterated query, the iterated query will try to build the parsing table. Well, in the first iteration of our Q loop, of our iterated query, we will of course see all the contents that has been produced by the base case query, by Q0, by the zeros iteration in a sense. And these are exactly the rows that will be seen in the first iteration of Q loop. Okay, so these are indeed the basic parsing facts that could be derived from individual characters in our input. And well, yes, we would find mult and fact in there. And according to the parsing rule prod maps to mult fact, we could indeed derive the prod non-terminal in the next and pass that on to the second iteration of our Q loop query. So the first iteration could join these two entries in the parsing table to produce a result that is then available to the second iteration of the Q loop. And that of course would be this entry here. Okay. To proceed past reconstruction and parsing, well, we would like to derive this particular non-terminal from this particular parsing rule here. Okay, but well, the prod part is indeed present and it indeed can be seen here in the second iteration, but the fact that term 3.3 has been derived by the zeros iteration, by the base case query Q0, is indeed unknown to the second iteration to our Q loop query. It would be missing. This is what indicated here with this cross. And we would not be able to derive this non-terminal and to pass it on to the third iteration of our Q loop. This is a real problem here. We need longer term memory. We need to remember that back then, these parsing facts, for example, term 3.3 has been derived. Okay, and this is the bigger point of this particular example. It's one particular example where we need to make sure that our recursive common table expression has long-term memory when it comes to the evaluation of this Q loop query. We need to re-inject, or need to make sure to not forget to re-inject knowledge that we have discovered earlier and to make that available to later iterations of our Q loop query. And here's one SQL template that could help us to do just that. All right, so that would be a SQL template that would help us to construct a recursive common table expression with long-term memory. Okay, well, it has all the ingredients that you would expect. Of course, it has a Q0 base case query, and of course, it has a Q loop iterated query part, but there is more to that, right? So we will first make sure that the result of the base case query and also the result of the Q loop query, of course, that these carry explicit iter columns. Okay, so here's the iter column. We initialize that with some arbitrary value, 0, for example, and indeed you will find this iter column here in the result of the entire common table expression. We have seen these iter columns over and over again. Maybe Q0 indeed generates such an iter column already, so there would be no need to use this tiny wrapper here to add one iter column to the result of Q0. If it's not there, use the wrapper. If Q0 itself already produces an iter column, then that's fine and there is no need to add another. Okay, this is the first bit. The second bit is this. Instead of only producing new rows in our QLoop query, newly discovered knowledge, we will also use the current state of the working table of our recursive table and add this to the newly discovered knowledge. Okay, so this would be the old knowledge. This would be the new knowledge that we discover. Both will be thrown into one pot here. Okay. Once we've done that, well, again, we will have a wrapper that just adds the iter column. In this case, an increasing iter column to all the columns that this union has produced here. All right, because we will have a new iter column. Because we will have a new iter column in each new iteration, indeed, all the rows that we are producing here will be indeed new rows. They will be considered as new rows by the union or semantics of our back-based recursive CTE. Okay, so increasing the iter value is really crucial here. So everything that we compute here will be understood and will be seen as new knowledge that is indeed passed on to the next iteration. And this is exactly what we needed. Everything that has been discovered before and the new stuff, all of this will be passed to the next iteration. And the next iteration will have access to all of the stuff, the long-term memory stuff and the most recent stuff that has just been discovered. Okay, as you can see, we are accessing the recursive table T here at this particular position. And of course, we can expect QLoop to refer to the recursive table T. It would be very strange if QLoop wouldn't refer to T in this setup. So there is already two references to the recursive table T. One explicitly visible here, one implicitly and hidden inside the QLoop. So what we need is our old friend, the with here, the non-recursive with that makes sure that we can refer to the name T multiple times without the system complaining that we are violating syntactic restrictions by SQL. But that's all there is to it. This would be the SQL template for recursive common table expression that has long-term memory, that uses re-injection of old knowledge. Here's the re-injection. Once we've done that, we can come back to our parsing example and see how things look now. So everything looks the same in the first iteration of our QLoop query. Well, we have added this iter column here. This has not been there before. So everything that we've seen here has indeed been discovered by the base case query in the zeros iteration of our computation. And we know all about these parsing facts already. We could use the mult and fact entries here to derive new knowledge, about a new left-hand side non-terminal that could be derived. And indeed, it spans the input indices from 4 to 5. Everything else, all of these entries will be re-injected and added to that particular new result to form the entire result with long-term memory. So in iteration 1, right, we have found some new stuff here, and we are re-injecting the old parsing facts using our re-injection technique with a new iter value, so that indeed the system sees that all of this stuff here is indeed new. Nothing of this shape has been seen before. Mult for 4 has been seen before, but back then it carried the iter value 0. Now it carries the iter value 1. Okay, so everything is there. Everything is present that we need to now derive the new non-terminal term here that will span from input indices 3 to 5. And we will base this derivation on the newly derived prod non-terminal and on the older knowledge that term 3.3 has been derived some iterations before. That's perfect. So Of course, we will add term to our result, but everything else that we found in the second iteration of our Q-loop query will also be re-injected. And based on this entire knowledge, we will be able to derive more parsing facts, more non-terminals in the further iterations of our query. So now everything is in place to describe the parsing algorithm that we will implement. Actually, I think it should be obvious and apparent by now. The parsing algorithm that we can build on these discussions is the Cocky-Young-Casimir algorithm, or CYK algorithm. Okay, this is an algorithm that indeed builds the parse tree bottom up, and of course it relies on formally discovered parses, partial parses. Partial in the sense that only parts of the input string could be mapped to non-terminals. All right. Indeed, this will build this particular parse tree. It's the parse tree form that we have discovered before. As you know now, the SQL template with long-term memory for our common table expressions will add an iter column to that. All right, so in the base case query, we would just look at these rules that allow us to derive the first left-hand side non-terminals from simple terminal in symbols in the input. So whenever we see such a terminal in the input at indices from to 2, that would be a parsing fact that we add to our parse table. This is very simple, and it's been done in the Q0 base case query. Later on, in our Q-loop query, well, we would look at pairs of parsing facts that have already been derived. So let's assume that these are two parsing facts that have already been derived in earlier iterations. From that, we could derive a new parsing fact, namely this one, given that two conditions exist. Of course, there must be a rule, a grammar rule of this shape. So this left-hand side 3 can be derived from two left-hand sides, two non-terminals, LHS1 and LHS2. And such a rule is indeed found in the grammar. And we have to make sure that the input spans that are have been used to derive LHS1 and LHS2, that these are indeed adjacent in the input. So only if these are adjacent in the input, they can form a new longer partial parse that can then be attributed to LHS3. So that would be the second condition to check here, whether indeed the end of the first partial parse immediately is immediately next to the beginning of the second partial parse. And that's about it. This is all there is to it. As you can see, in our Q-loop query, we will look at the parse table 2 times to derive and to extract two different path facts that have been derived before. This is a self-join of the recursive parse table with itself. This is nonlinear recursion, but we know how to deal with that since our discussion of cellular automata. And that would be the entire parsing algorithm, right? So we have omitted the re-injection code here, but everything else is present. This would be the Q0 query. It would only consider those grammar rules that are indeed considered with terminals. All right, it would check along the entire length of the input whether such a terminal is indeed being found in the input. If it does, then we are in the position to create the appropriate parsing fact. Other than that, we are in the Q-loop part of the entire query. And well, here you can see the self-join of the parse table with itself. We would extract two parsing facts called L and R from these parse tables. We would check the two conditions. Well, we would check that indeed the spanned inputs are indeed adjacent to each other. And we would check that there is a particular grammar rule, that matches the non-terminals that we have extracted from the parse. If all of this is indeed fulfilled, well, then it's time to produce a new parsing fact that spans the entire input from the beginning of the left to the end of the right-hand side parse that we have extracted here from the parse table, and that would be the new parsing fact. So indeed, this parsing algorithm, the CYK formulation in SQL, is very simple and actually I think quite declaratively to read, very easy to read and understand once all the previous preliminary discussions are in place. All right, I think that's about it. Let's quickly switch over to the terminal and see that this indeed works as expected. Here we are in the terminal, and what you will see here, of course, is, for example, the relational encoding of our Chomsky normal form grammar, which only admits grammar rules of these two forms. So NT would be a non-terminal, sims would be a terminal here. All right. So let's look at the table that we use to store the grammar. It's just the table that we have proposed on the slides. It will have a left-hand side column that stores a non-terminal, and then it would either store a terminal for the first type of grammar rule, or it would store two non-terminals on its right-hand side, right? To check that only this or only these two are being populated and the other part indeed is null, I've included this constraint here, this check constraint in the table. But, well, yeah, this is not material to our discussion of recursion in SQL. And there's the start column that will tell us that this left-hand side symbol is indeed a start symbol. All right. Well, you see that I'm using these non-terminal and terminal types here, but they are indeed only synonyms for the type text. So terminals and non-terminals are simply represented as text in my sample application here. So let me define all of this, all the types, and then also the table. All right, now we are only left with filling that particular table. So let's take that grammar, the grammar that you've seen on the slides, and convert it into Chomsky reduced normal form. That would be this particular form, also seen on the slides. And this is the insert statement that encodes this grammar inside our table. If we look at the table now, you will recognize the table that we have seen on the slides. Indeed, expression is the start symbol, as we can see. And our check constraint makes sure that we either look at rules of this form or rules of this form where there are two non-terminals on the right-hand side. Okay. Some sample input to parse, exactly the input that we have considered on the slides again. Well, and then here you find some comments that reiterate on the parsing idea, on the construction and the invariance of the recursive parsing table. All right, so all of this is just a repetition of what we've discussed so far, and this is the core of the SQL code. You see that we indeed build this 3-column parse table that also carries the iter column. This stems from our template of long-term memory recursive CTEs. So in fact, we are operating on a 4-column table here. Okay, this would be the Q0 base case query. All right, taking care of recognizing terminals and injecting the first parsing facts into our parse table. Well, and then this is the recursive part of our table. You see that we are preparing for multiple references to our recursive table here, just as usual. Then you see the re-injection part here, re-injecting all parse tree knowledge. And this would be the core of the CYK parsing algorithm that extracts two parsing facts, makes sure that they are adjacent and correspond with actual grammar rules, and then constructs new parsing facts from old facts. Okay, well, we will stop iteration at one particular point. We could use the higher iteration value here, but 4 suffices for the experiment and the input that we are using in this particular example. And then we could just run the whole thing. Here I will just dump the entire parse table that has been constructed. Let's try that. There you go. So indeed 4 is the last iteration that we were considering. These are all the accumulated parsing facts that have been found during our parse. As you can see, through the re-injection of old parsing knowledge, indeed stuff can be found here that has obviously been discovered in iteration 0 back then. If we would scroll up now, we would see iteration 0. We will do this in a second, but as you can see, very old parsing facts that have been derived from individual character entities in our input string, they are still present here. But of course, there's also the more recent stuff. The most recent stuff, for example, is present. This is the top of our parse tree. The non-terminal expression could be derived from the entire input string here. All right. And these are nodes that would be found in the lower levels of our parse tree. Okay. All right, this is iteration 4 where everything is complete. There are some of the intermediate iterations here that derive the intermediate layers of the parse tree. All right, the further we get to the start of the table, the less rows we will find per iteration because, well, in each iteration has added new parsing facts, and the re-injection makes sure that nothing will be forgotten. All right, so that would be the output of the 0th iteration of our base case query, where we only find parsing facts that are based on single characters. All right, so from this table, it's easy to add some post-processing that indeed checks that our parse was successful, and this is the last bit I'm trying to show you here. All right, so given this parsing table and the grammar, we would just check that the parsing table contains one parsing fact that says, well, we could start at the first index of your input. We could end our parse at the last index of your input, which is just the entire length of the input. All right, and then we would check that the rule or the non-terminal that has been derived from this particular parsing fact is indeed one of the start symbols of your grammar. If these conditions are fulfilled, well, then this entire check will be true. And what we will output here is that the parse went through and was successful. And indeed, yeah, this is the input. This is the input 1 plus 1 times 1 that could be parsed successfully. So if I would now make this a different input, this grammar currently cannot recognize subtractions, and we would start the parse again. Well, we will find an empty output here, which is equivalent to an invalid parse. Okay, so this is context-free parsing expressed as the CYK algorithm in recursive SQL with re-injection, long-term memory, and multiple reference to the parsing table. As you can see here, there's even 3 references. I think that this indeed qualifies as advanced SQL. And I hope that you enjoyed our tour de force through recursion in SQL. I know that the queries that we were constructing during the course of this particular chapter look nothing like the queries that you would normally find in SQL textbooks. But this is the entire point of this particular lecture. This is not the normal select from where join expressions. This is about advanced uses of SQL and trying to push the limits of what the language can give us and try to explore what kinds of computations can indeed be dragged into the database and have computation executed close to the data. All right, so this concludes chapter 6. It has been lots of fun for me. There's one more chapter to go in this particular lecture. It will be a shorter chapter. It will be on PL SQL, a complete different flavor of programming SQL. Also super interesting. I hope you stick around for Chapter 7, which will then conclude the entire course. Thank you for your interest. See you soon. Bye-bye.